This video is about weak acids and bases. You should already be able to write mass-action expressions, the K equals equations, but also calculate the pH of a strong acid or base from the last video. And then in this video, you should also be able to calculate the pH of a weak acid or base. So the question of the video is, trimethylamine is a foul-smelling volatile organic compound that formed during the decay of plant and animal matter. Just a little side note, if you had not thrown away your holiday pumpkin, it is time, right? So this would form as the pumpkin decomposes. The pH of a 0.5 molar dilute solution of trimethylamine in this pumpkin is 11.75 at room temperature. So we want to know what the basicity of the substance is. We can tell it's basic by the pH, but like how basic is it exactly? What is the molarity of the base? So we have to go through dissociation constants, or K equation. So normally if we're given an equation for water with any acid will form the acid ion and the H3O plus ion, and that equilibrium expression would be the two ions on the top products over the reactants, HA. Water is not in the equation because it is a pure substance. This is also known as Ka because it's the K of any acid. So all these Kas follow the same rules we learned about all Ks, that if K is high, that means it's very product favored and it forms a lot of ions in this case. And those ions are the hydronium ions, which makes it very acidic. If the K is very small, like you see these values are particularly small, that means the acid is really weak. It mostly stays in the HA form and does not form ions, which do not conduct electricity, do not attack other chemicals, and do not react as well. And so you can see all these are considered weak acids because the Kas are small, there's less ions, and as you go down the list, they're getting weaker and weaker and weaker. You can tell by the negative exponents increasing. So if we were to use an example of how to calculate the pH of a weak acid, here's an example, the pH of 0.3 molar of acetic acid. If this was an acid like HCl, hydrochloric, all you would have to do is negative log the 0.3 molar, and you would get something less than 1. But because this is a weak acid, it's not going to form as many ions as the strong acid would have, and you can't just negative log the 0.3. Instead, what you have to do is put it into an icebox formula. So that's why they gave you the Ka as a huge hint. You're going to have to use that K expression. So taking that equation, you can write your Ka as the ions over the acid, and you can write your icebox in the same order as the reaction was given, with an initial concentration of 0.3 as given in the question. No ions are present. The change has to go to the right because you have the acid form, but you don't have any ions yet. So you're going to take 1 away from the acid and add 1 for each ion because it's a 1 to 1 to 1 ratio of moles. And then rewrite it as an equilibrium. 0.3 minus x, 0 plus x is x, and 0 plus x is x. Now we can plug these x's into the top part, so x times x, and 0.3 minus x into the bottom part, and then reuse the Ka that we were given on the previous slide, which was 1.8 times 10 to the minus 5. And we can resubstitute that into the Ka expression. So if we do that, it looks like 1.8 times 10 to the minus 5 equals x times x, or x squared, over 0.3 minus x. If you solve this as is, you'll have to cross multiply and distribute the 1.8 times 10 to the minus 5 through this entire equation, and then solve for x squared, x, and the values, and then do a quadratic formula. But if you remember from the last unit in equilibrium, we usually try to find ways to avoid doing any type of quadratic. And the way that we're going to do that here is only since the Ka is particularly small, we can say that when we do this, the x is going to come out pretty small when we start multiplying. And so if the x is really small, it probably won't really affect the 0.30 number. In that case, we're going to avoid the minus x, not the x squared because we need an x somewhere, but the minus x, the change is going to be really tiny because the Ka is really tiny. That makes it so that we can just cross multiply the two values and have that equal to x squared. And then once you multiply them, you can square root both sides, get x alone. But remember that x is not your answer. X is how many ions you had, right? So if you go back to the icebox you have, x is how many hydronium ions you have, and that's not what the question asks. It asks how the power of that hydronium, or pH. So I know it's probably roughly around 3, but if I actually negative log it, I get 2.64. If you remember, if this was a strong acid, I would have gotten less than 1 as my pH. Because it's a weak acid, the pH is much higher, showing that it's not forming as many ions and is not as reactive. Let's do that again for a different acid. So here's hydrofluoric acid, which is one of the weaker acids as well, and that's why I gave you a Ka. It was a big hint. So what we're going to do, I'm going to do it all on one screen. Maybe it'll be easier to see. This is the acid dissociation reaction. Remember, water does not have to be written. It could be written above the arrow so you don't accidentally put it into your Ka if you want, or your ice box, all right? It's not going to affect that. So initially a 0.5 of the acid and no ions. It's going to shift to form the ions. You notice the ice boxes all look pretty much the same with just a different initial condition. Then we're going to plug it into our Ka. So the Ka is given in the question, and it's x times x over the reactant's 0.5. I didn't even write minus x because I know it's going to be eliminated since the Ka is so tiny. When I cross multiply, I get something like this, and then I square root both sides, and I get 3.4 times 10 to the minus 5. Again, that is a value, square root, 5.8 times 10 to the minus 3. That is the value of hydronium. It is not the pH. The power of the hydronium is somewhere around 3, but if I actually negative log this value, I can get 2.23. So we can see that it varies with what the concentration of the acid is and the identity of the acid. I want to do it one more time, but I want to change the concentration of HF. Instead of going 0.5, let's do 0.9. Let's think for a second. If I increase the amount of acid in the solution, do you think the pH will increase or decrease? Again, if I increase the amount of acid, will the pH increase or decrease? Let's prove it. So we're going to do a very similar question. I'm just going to do 0.9 molar. And I'm going to plug that into the very standard ice box that we've been seeing over and over. Then plug that into the Ka expression, which you're seeing is always the same thing. It's Ka equals x squared over the molarity. I'm going to cross multiply and then square root that answer to get x alone. Again, this x is the hydronium concentration and not the pH, so I have to negative log this value to get a value that is the power of the hydrogens, or 1.61. If we compare that to the previous answer, which was 2.63 if I remember, or 2.23, we can see that as I add more acid, the pH decreases. And that makes sense because acids have lower pHs. The more acidic it is, the lower the pH is. So it's important that you know how that works with pH scale, but also how to calculate it. Let's do it one more time for nitrous acid, which is a weak acid. HNO3 would have been strong, but HNO2 is a little weaker. We're going to plug in our values into an ice box. I don't know why the ice box didn't come up right away, sorry. So it would be 0.36 molar, and then you're going to shift to the right. See how similar this is every time? So some students start to avoid writing the ice box since you don't really get credit for it. And they just skip right to 4.5 times 10 to the minus 4 equals x squared over the molarity. That is up to you if you want to do that. I don't recommend it because in the long run, when we start changing this to bases and salts, that might change a little bit. When you solve for x, it becomes 1.3 times 10 to the minus 2 molar. I'm going to negative log that to get a pH. So this is really standard. We've seen quite a few of them. There's nothing to be worried about. It kind of goes through the same process over and over. A different type of question they might ask is if you have this double-headed arrow and the HNO2 is competing with the HF. There's two acids on both sides. They might ask you which one is favored. Does it go more towards the forward reaction and make more NO2 and HF? Or does it go more reverse and make HNO2 and F minus? And the only way to know that is to be giving the Ka values. These Ka values tell you how strong or weak the acid are. In this case, both of them are weak. But the one that's particularly a little bit tiny bit weaker, since they're both 10 to the minus 4, is HNO2. It's only 4.5 versus 6.8. Since HNO2 is slightly weaker, it doesn't ionize as well. Since HF is a little stronger, it ionizes a little bit better. So I would argue that this reaction reverses a little bit more than it goes forward because HF will form fluoride ions more often than HNO2 forming nitrate ions. Another question they might ask is calculating percent ionization. All that means is how many ions you have, H3O plus ions, in this solution versus how many you had started with. So in a previous example we did, we had done 0.36 molar HNO2, that should say, and it had 1.3 times 10 to the minus 2 molar hydrogen ions, or hydronium. All you would have to do with that is now plug those in as your numerator and denominator and times by 100. What you're noticing is it's a very small percentage that's ionizing, and if there's 100 particles, not even 4 of them are forming ions. That's pretty true for all acids that are weak. Weak acids ionize less than 5%. Strong acids usually ionize more than 95%. They're very distinctly different. So if we look at it like this, if there was 100 particles, only 5 of those particles or less of any weak acid are going to actually be acid ions. Weak bases are pretty much the same way. They're going to form water with water, a conjugate acid, and the hydroxyl ion. And the Kb is going to be the ions, so the NH4 and OH on the top, and the base on the bottom. Again, the water is not there because it's a pure liquid. Similarly, their Kb's are very small numbers because they're weak. So the weaker they are, the more smaller Kb's are because they're forming less ions. So in this case, ammonia being one of the stronger of the weak bases here, and something like pyridine being one of the weakest on this list. So if we were to do this, it's a very similar setup as an acid. You're just going to write your reaction out, do an ice box. So your initial conditions switch to the right side, and your equilibrium conditions when you add them up. Notice that again, we can avoid the minus x because the Kb is really, really tiny. And so when we plug them in, we get x times x, or x squared over 0.15 equals the Kb given. We cross multiply and find the x alone when we square root to get 1.6 times 10 to the minus 3. Again, this is not the answer. This is just how many ions I have. If I want to know the power of the hydrogens and I have the ions of the hydroxide, I have two ways of figuring this out. I think the easiest way would just be negative log that value and then subtract it from 14. And so I get a pH of 11.2, which makes sense for a base because it's higher than 7. A lot of people forget to subtract from 14, so just consider your answer before you move on. Another way of doing this would be to divide it from the Kw, 1 times 10 to the minus 14th, and then negative log it. So if you wanted to do it that way, remember our box of pH, you could do it two ways. Ka and Kb are related. So if you were given the wrong K, like if you were giving a Ka but you needed a Kb for a base, or giving a Kb and you needed a Ka for the conjugate acid, they're related. So if you look through these, HF and F minus versus acetic acid and acetate ion, what you'll notice is if you multiply these two numbers together, you'll always get to Kw, or 1 times 10 to the minus 14th. It's very similar to how hydrogens ions and hydroxide ions also multiply out to Kw, or 1 times 10 to the minus 14th. Everything is interrelated. So let's go back to the question of the video. In this pumpkin, which is a 0.5 molar solution of trimethylamine, which is not one of the strong bases, what is the basicity of the substance if the pH is 11.75? What we can realize is if the pH is 11.75, that means the hydroxide concentration is 10 to the minus, I don't know why I don't have that as an exponent, 14 minus 11.75. And the reason being, I'm just going to fix it while you're here. This should be an exponent so that you don't have to read it a little bit strangely. There you go. And that one too. Sorry. Right. So when you are thinking about it, it's going to be 14 minus the pH to get the pOH. So, and then raise that to the 10th power. So you get a really small concentration. So that it's very, very dilute, the amount of base. Even though the amount that you dissolved in there is a little bit higher, the amount of base that's coming off is a lot less. We can also figure it out by Kb if I want. The Kb would be the products over the reactants. And since I know what those values are, now I know it's the hydroxide is 0.00562. For every hydroxide, there's one of the ions that is the positive cation, so that's also 0.00562, which is why we usually have x squared there. And the molarity was originally 0.5 as given in the question. I can see the Kb is pretty small. Again, that being a weak base, I was expecting a low Kb. Another thing I can look at is ionization. To figure out how basic it is. So if I take how many hydroxide ions I have, 0.00562 molar, and divide by how much the original conditions were 0.5, and times by 100, I notice that it ionizes less than 2%, 1.12%. So for every 100 particles of this crazy, rotten, disgusting smelling volatile organic compound you have, only 1% of them are the base ions that are giving that smell. So at this point, you should be able to calculate the pH of a weak acid or a weak base.